Welcome back, everybody. In this video, we'll be continuing our work on section 3.6 with finding zeros of polynomials. In this one, we're going to start by taking a look at something called the rational zeros theorem, or rational zeros test, it's sometimes called. So first of all, just as a reminder, what rational zeros are, or what rational numbers are, is just fractions, basically. So as far as rational zeros, we're talking about numbers like 3, or -1/4, or 5/8, or 11, right? So the things that we're not talking about would be zeros like pi or the square root of 7, okay, which are irrational numbers. This part, we're just dealing with zeros that you can express as a fraction, so rational numbers. Okay, so what the rational zeros theorem says is if you have a polynomial, and it's written here in kind of like formal language, it's a sub n x to the n. So the degree on this thing is n. A sub n is the leading coefficient, okay? X to the n, first term. A sub n x to the n is the first term. A sub n minus 1 x n minus 1 second term, and so on, all the way down to a1x, a0. Okay, if it has integer coefficients, so that means that all the aj's are integers, okay? You don't have like 5/8 x squared or something. If they're all integer coefficients, then every rational zero, so all the zeros that are rational numbers, has the form p over q, so they're fractions, where p is a factor of the constant term, a0, and q is a factor of the leading coefficient, an. Okay, when the leading coefficient is 1, the possible rational zeros are all the factors of the constant term. So that's kind of a lot. So the best way to see how this goes is with examples. All right, so let's say that we wanted to know the possible rational zeros of 3x squared minus x minus 4. So they're all going to be fractions, and the possible numerators would be factors of 4. So what are all the factors of 4? Plus and minus 1, plus and minus 2, plus or minus 4. For denominators, factors of 3. 3 is prime, luckily for us, so its factors are only plus and minus 1, plus and minus 3. Okay, so what all does that give us? It gives us -1 and 1, -2 and 2, -4 and 4, and then for denominators of 3, -1/3 and 1/3, and then -2/3 and 2/3, and then -4/3 and +4/3. Okay, so then if you're wondering, okay, well, this thing has degree 2. I thought it only had 2 zeros. How can it have all these? It doesn't, okay? This is what the possible rational zeros are. So could f of 5/8 be 0? No, because it's not among these. For this one, it happens to be a degree 2, so we would be able to tell what the zeros are right away using the quadratic formula or via factoring. They're going to be among these. So let me go ahead and get them for you. All right, it turns out that the zeros end up being 4/3 and -1. Okay, so with this one, since it's a quadratic, we could just use the quadratic formula and find what those zeros are. But for polynomials like the next one, where it's higher degree, we can't just like do that, right? Because there's no fifth power version of the quadratic formula. So the rational zeros theorem gives us a place to start as far as what could the possible rational zeros be. So for this one, it's degree 5, so there would be 5 total zeros, but some could be irrational or maybe even complex numbers. But as far as the rational zeros, here's what's possible. They're fractions. Their numerators are all factors of 8. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Those are all the possible numerators. The denominators, luckily, well, not so luckily this time, 12 has a lot of factors. So plus and minus 1, 2, 3, 4, 6, and 12. Okay, so this one is going to have a whole lot of rational zeros as factors. But we would have to work our way through checking some of those to see if there are rational zeros to this degree 5 polynomial. Okay. All right, in the next example, what we're going to do is actually find the rational zeros. In the first two examples, we just found out what the possibilities were. In this one, we will actually find out what those zeros are, and then we'll go ahead and factor f as much as possible. Note that this thing has degree 3, so that's not the kind of thing we usually factor, but here we're going to be able to. So first thing to do is write down what the possible rational zeros are, according to the rational zeros theorem. So the factors of 3 will make up the numerators. So plus or minus 1, plus or minus 3. For the denominators, it's just going to be factors of 2. So that will be plus or minus 1, plus or minus 2. So as far as integers, I would start with the integers because they're going to be easiest. We'll have -1 and 1, -3 and 3. All right, that's everything with denominators of 1. And then where we have denominators of 2, we'll have -1/2 and +1/2. And then for 3's on top, we'll have plus and minus 3/2. So -3/2 and +3/2. All right, so I would start with the integers because they're going to be easiest to calculate with. So I'm just going to start at -1 and work my way over. You can plug in these numbers into this f and compute if you want. I'm going to do this using synthetic division, partly because I think it's easier, and partly because our goal is to get this thing factored. And if I go ahead and do the division, then that will have completed one step for us. Okay, so 2x cubed, 3x squared, -8x, and a 3. Okay, bring down the 2. Okay, so we're going to multiply and add. So -1 times 2 is -2. 3 plus -2 is 1. -1 times 1 is -1. -8 plus -1 is -9. And I can tell right now it's not going to come out 0, but we'll finish it. -1 times -9 is +9. That gives us a remainder of 12. So -1 didn't work. Let's try 1. Okay, 2, 3, -8, and 3. Okay, so 1 times 2 is 2. There's 5. 1 times 5 is 5. This is looking better. -8 plus 5 is -3. 1 times -3 is -3. So there we go. So we've gotten that. We've found out that 1 is a 0. So since 1 is a 0, that means that x minus 1 is a factor. So our f of x is starting to factor as x minus 1. The other factor is going to come from our quotient row of that last synthetic division, which is the reason I'm using synthetic division for this instead of just plugging in the numbers. So this will give us 2x squared plus 5x minus 3. Okay, so there's our factorization, but I want to check and see about finding the zeros for the quadratic part right here. So we're going to do that. I'm going to do it down here, and I think I could do this by factoring. So I'm going to factor this by grouping. 2x squared plus 5x minus 3. To factor by grouping, I want to find two numbers that are going to multiply to what 2 times -3 is. 2 times -3 is -6, and I want them to add up to 5. So 6 and -1 looks like they'll do it. 6 times -1 is -6, and 6 plus -1 is +5. So we're going to take that middle 5x and write it as 6x minus x, and then factor that by grouping. So common factor of 2x will come out, making x plus 3. A -1 will come out, leaving behind x plus 3. Okay, common factor of x plus 3 comes out, leaving behind 2x minus 1. Okay, so that is how we're going to finish the factorization. X minus 1 we had before, x plus 3, and then 2x minus 1. Okay, so that takes care of the factorization. And then the zeros are 1, -3, and -1/2. And you can obtain those by setting each of those factors up above equal to 0. All right, so we found all the possible rational zeros, and then I just started trying some of them. And I got lucky. One turned out to be a 0. And so that gave us a degree 2 quotient, which fortunately you could have used the quadratic formula or factored. I chose to factor on this one. Notice that for our zeros, we ended up with 1, -3, and -1/2, which are all in this row of possible rational zeros that we had come up with. Okay. At the end of that, that is the end of that. All right, so one thing that is important to remember is that the rational zeros theorem helps you know about rational zeros. It doesn't tell you anything about irrational zeros. Okay, for example, take a look at f of x, which is x minus 3 times x squared minus 10. If you multiply that out, you're going to get x cubed minus 3x squared minus 10x plus 30. Turning around and trying the rational zeros theorem on it, these would be the possible rational zeros. Okay, and it turns out, though, that the only rational zero is 3. It has 2 irrational zeros, which are the square root of 10 and negative square root of 10, but it doesn't say anything about that. Okay, all it tells you is if there are rational zeros, then they're going to be in this list, but it may or may not have any irrational zeros. Okay. All right, f has 2 irrational zeros of plus and minus square root of 10. One thing worth noting, an interesting fact, is that irrational zeros, like that plus and minus square root of 10, those occur in what's called conjugate pairs. Notice that it's the same square root of 10 and minus square root of 10 with opposite signs. Those are what's called conjugate pairs. And that's going to happen whenever your equation has rational number coefficients. All right, but the important piece to take away from this particular slide here is that the rational zeros theorem will give you some clue about rational zeros. It doesn't tell you anything about irrational zeros one way or the other. You'd have to have something else to help you with that. All right, so another kind of useful fact from this section is something called the fundamental theorem of algebra. Here, when they say fundamental, they don't mean fundamental like easy. They mean fundamental, like kind of in the sense of importance. And what this says basically is that if you have a polynomial of degree n, then it's going to have at least one zero that is a complex number. As it turns out, it has exactly n zeros if you count repeats, and it has exactly n linear factors. So put in more everyday language, if you have a nth degree polynomial, it's going to have n factors. If you have a degree n polynomial equation, it's going to have exactly n solutions. If you count repeats and if you count complex number solutions. All right, so the next part has to do a little bit more with complex number solutions, and that is what's called the conjugate zeros theorem, or complex conjugate theorem is what our book is calling it. So let's take a look. Okay, according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree. What that means is like your quadratic functions, they're degree 2. When you factor them, you get 2 linear factors. If you have a degree 3 polynomial, you're going to get 3 linear factors, and so on. Okay, each factor is going to be the form x minus c, where c is a complex number. And then furthermore, and this is the part that is important for this section for right now, is that if you have a polynomial with real coefficients, and all of ours will, and you have one complex zero, a plus bi, then its conjugate, a minus bi, is also a 0. Okay, so another way of saying that is if you've got a polynomial function p, and you know that a plus bi is a 0, then a minus bi is a 0. Or complex zeros occur in conjugate pairs. Okay? All right, so just as a quick example of that, a nice easy example, the equation x squared equals -4 has two solutions, 2i and -2i. Okay, those are two complex conjugate solutions. All right, so let's say that we want to create a polynomial that has degree 3 and has real coefficients that has zeros of 2 and 1 plus I. So if it's going to have a 0 of 2, then that means that x minus 2 will have to be a factor using the factor theorem. If 1 plus I is going to be a 0, then it's going to have a factor of x minus 1 plus I. Again, using the factor theorem. The thing is now, if we stop right here and just multiply this thing out, then our expression is going to end up having i's in it, and it won't have real coefficients. We're trying to make a polynomial that has real coefficients. As a consequence of this conjugate zeros theorem, if we want our polynomial we're making up to have real coefficients, then we need to add in the conjugate of the existing zero. So we'll have x minus and then 1 minus I. Okay, that will make it so that it does have degree 3, which was part of the requirements. And also, as we'll see when I multiply this out here in a minute, that we're going to end up with just real coefficients. So that's going to be pretty great. All right, and this will be almost the end. Okay, so I'm going to take and rewrite this a little bit just to make our multiplication just a little bit easier. So how I'll do that first is I'm going to distribute the negative that you're seeing in here. So we'll have x minus 1 minus I and x minus 1 plus I. Okay, now we're going to use the associative property and write that as x minus 2, x minus 1 in square brackets, minus I, and x minus 1 plus I. Okay, so the reason that I wanted to do that is basically so that I can use the difference of squares formula to help us multiply this. If you multiply a pair of binomials that look like a plus b times a minus b, you end up with a squared minus b squared. That's the difference of squares formula. So we will have x minus 2 in the front. And then this is difference of squares. We will have x minus 1 squared minus I squared using this difference of squares formula. We use that right here. Okay, remember that I squared is equal to -1, right? Okay, so the x minus 1 squared piece is x squared minus 2x plus 1. And then minus I squared will give us another plus 1. Because minus I squared is minus, and then the I squared itself is -1. So that will give you ultimately a second kind of plus 1 here. We're almost done. X minus 2. X squared minus 2x plus 2. Okay, so you can see now that all the i's are gone. When we keep multiplying this out, we're going to end up with just real numbers. So I'm going to go ahead and multiply this out the rest of the way just so that we have it. I'm going to do this using the distributive property. I'm going to multiply the x throughout and then the -2. So we'll have x times x squared is x cubed. We'll have minus 2x squared plus 2x. Now we're multiplying the -2. We'll have -2x squared plus 4x minus 4. Okay, and then let me combine like terms. We'll have x cubed. We'll have minus 4x squared. We'll have 6 x's and minus 4. Okay, so that finally will do it. That has the correct zeros. It has the correct degree. All right, so finally for this, if we want to make this thing so that it has a leading coefficient of 2, right now the leading coefficient is a 1. I can't just change that and call it 2x cubed, right? Because that's going to change what the zeros are. However, we can multiply the whole polynomial by 2. And then that will serve to just stretch the graph vertically, but it won't change what any of its zeros are. So we'll call it f of x, 2x cubed minus 8x squared plus 12x minus 8. Okay. All right, so that doesn't finish the section for us, but it does finish this video. So let me know if you have any questions, and have a great day.